Spooky action at a distance explained. Introducing spin. Before we go into what spooky action at a distance entails, let's chat about spin. Particles have a property called spin, and when the spin of a particle is measured, it will be either spin up or spin down in the axis that it is measured. Let's take an example. Say we take a particle and we know that it is spin up in axis 1. What happens if it is measured in axis 3? You might expect it to indicate no spin at all, as the axis is perpendicular to axis 1, but it will. It will be either spin up or spin down, but across a number of measurements, the particle will indicate spin up and spin down equally across axis 3, cancelling the results out. So what happens in axis 2, which is a 60-degree angle to axis 1? As axis 2 is closer to axis 1, the particle will indicate it is spin up 3/4 of the time and spin down 1/4 of the time. Entangled particles. Entangled particles describes the phenomena when two particles become connected in such a way that when the property of one particle is changed, an instantaneous change in the property of the other particle occurs. Entangled particles have the opposite properties, so when one particle is spin up in one axis, the other particle will be spin down in that same axis. A pair of entangled particles could be separated by an entire universe, and when one is measured to be spin up in axis 1, the other one will be spin down in that same axis. Einstein called this phenomena spooky action at a distance. 2 explanations for entanglement. Quantum mechanics explains the behavior of entangled particles by saying there seems to be some sort of instantaneous communication that happens when one particle's spin is measured, which causes the other particle to take on the opposite spin. Einstein offered up an alternative explanation. He said that during the entanglement process, it was decided by the particles what spin they would have in all axes to ensure that they always had the opposite spins to each other. Einstein's explanation gave us 2 scenarios. One where particle A could decide that it would show spin up in all axes and particle B would show spin down in all axes. Or another scenario where particle A decided to indicate spin up in axis 1, spin down in axis 2, and spin up in axis 3, while particle B decided to indicate spin down in axis 1, spin up in axis 2, and spin down in axis 3. There could be different combinations. Let's call the combination we have just described as combination 1, and we'll work our way through another combination, where particle A could decide to indicate spin down in axis 1, spin up in axis 2, and spin down in axis 3, while particle B decided to indicate spin up in axis 1, spin down in axis 2, and spin up in axis 3. But notice something. The combination is just the same as before, but only the particle name is different. We won't go through each combination here, but suffice to say that all possible combinations can be achieved in scenario 2 by changing either the particle name or the axis number. Bell's theorem. British professor John Bell then came up with a way of testing which explanation worked for the behavior exhibited by entangled particles. 2 entangled particles are separated and placed in detectors that can measure their spin in 3 different axes: axis 1, axis 2, and axis 3. Over a period of time, different axes will be chosen and the spins of the particles measured. This is what happens if quantum mechanics is correct. When particle A is spin up in axis 1 and particle B is measured in axis 1, it will be shown to be spin down. Now imagine an imaginary axis 4 in the particle B detector. As the particle is spin down in axis 1, it follows that it will be spin up in the direction of axis 4. As axis 2 and 3 are both at 60-degree angles from axis 4, the spin of particle B will indicate that it is spin up in those two axes 3/4 of the time, as explained earlier in the video when we first discussed spin. So in the experiment, when particle A is measured as spin up in axis 1, particle B will be measured in axis 2 or 3 2/3 of the time, as there are 2 out of the 3 axes that we are measuring, and as the particle will be spin up 3/4 of the time in those axes, the probability of particle B being measured as spin up is 2/3 multiplied by 3/4 equals half of the time. Mathematically, it was calculated that if quantum mechanics is correct about how spooky action at a distance works, both particle A and B will indicate the same spins 50% of the time and different spins 50% of the time. So now let's discuss what would happen if Einstein's alternative explanation is correct. Well, Einstein's explanation gave us 2 scenarios. One where the spin of particle A was spin up in all axes and the spin of particle B was spin down in all axes, and another where particle A was spin up in axis 1, spin down in axis 2, and spin up in axis 3, while particle B decided to indicate spin down in axis 1, spin up in axis 2, and spin down in axis 3. In scenario 1, as different axes are chosen and the spins measured, both particles would indicate different spins 100% of the time. In scenario 2, as spins are measured across different axes, there are actually 9 possibilities that could emerge. If axis 1 is picked for both particle A and B, the measurements show they have different spins. If axis 1 is picked for particle A and axis 2 is picked for particle B, the measurements show they have the same spins. If axis 1 is picked for particle A and axis 3 is picked for particle B, the measurements show they have different spins. Let's take a moment and tally up all the other possibilities. It's seen that if Einstein's alternative explanation is correct, the particles would show different spins 5/9 of the time in scenario 2. So no matter what scenario, if Einstein's explanation was correct, the particles would indicate different spins somewhere between 5/9 of the time to all of the time. So what were the results? Well, the spins were different 50% of the time, and the prediction of quantum mechanics held true, whereas Einstein's alternative explanation didn't work. And that is spooky action at a distance, summarized and explained. As always, this is a simplified explanation of complex ideas, and I hope you found this video informative and enjoyable and can use it as a springboard for further study. Remember to subscribe to LondonCityGirl for more interesting videos, and I'll see you next time.